Thanks very much to everyone for joining us today in our Concrete Sustainability Hub webinar series. Today, our topic is going to be about carbon uptake in concrete. And our postdoctoral associate, Hassam Azari-Jafari, is going to talk to you about some of the work that we're doing in the hub, looking at trying to quantify the environmental impacts of concrete, related to carbon uptake and how we put that in the context of other issues as well. But of course, many people know that we've been looking at carbon uptake in concrete for many years as a durability issue. So partly what we've asked Hassam to cover is how we try and balance both of those issues. So with that, I'm going to turn it over to Hassam. And one housekeeping note, everyone's muted, but there is a Q&A box in the lower right, and we welcome any questions, comments. If we can, we'll answer them in there directly, and if not, we've made sure to leave plenty of time for questions during the webinar. So with that, please take it away, Hassam.
Thank you so much, Jeremy, for the introduction. Hello, everyone. I hope you're all doing well. Thank you for joining this presentation. Today, I'm going to talk about the CO2 inhalation of concrete structure and the case studies that we have conducted on the US pavement network. So before starting this presentation and going through all the details and the mechanisms and the causes and consequences and the calculation, I would like to share some facts about concrete with you. You probably saw in different news press or research publications that, talking about living concrete, the concrete that can heal itself, talking about the self-healing capacity and the ability that we can get to concrete. Or, for example, about the concrete cancer, alkali-silica reaction, or the concrete can catch cancer and we have to cure that, and some folks and some researchers are working on that as well. Or for example, we can put concrete to sleep with and we can wake it up with some chemical admixture. So all these things make me think that is concrete alive? Well, if you want to hear my answer is yes. When I saw all these things that are similar to many different creatures, I think concrete is alive, and concrete, in fact, breathes. How can concrete breathe? It can inhale some CO2. So today, the topic of discussion that you would like to have is on the CO2 inhalation of concrete structures. And to do that, I would like to start briefly talking about our presentation outline. First of all, I will talk about the carbon uptake mechanism and the influential parameters on concrete carbon uptake. Then I will talk about the impact of carbon uptake on concrete properties, more specifically the hardened properties of concrete, and then different methods for measuring or estimating concrete carbon uptake, and then how it has been accounted in LCA, life cycle assessments, or environmental product declarations under the PCRs, more importantly, the European PCR that has provided a guideline for that. We will go through that as well. And at the end, I'll present the case study that we have done based on these information that I'm going to share with you on the US pavement network. So first, I'm going to talk about the mechanisms and the influential parameters. So what is concrete carbon uptake, also known as carbonation of concrete? When we have some moisture in our surrounding neighborhood and near to our concrete structure, the CO2 forms carbonic acid. The first equation that you can see here, the CO2 will react with water and will give us carbonic acid. And this carbonic acid, when it is exposed to concrete, can react with some hydrated products, here calcium hydroxide, and will form some sort of limestone or calcite or calcium carbonate here with some water here. So here is all the equations and all the reactions that we can that we will talk about in our today webinar. And it's all about the reaction of CO2 with the hydrated cement product, and we will call it natural carbon uptake. There are other types of carbon uptake, obviously, but here the focus is only on the weathering carbon uptake or natural uptake of concrete. that can happen during the use phase of concrete, when the concrete is hardened and under service life, and also at the end of life. So here I'm going to talk about different factors that can influence the intensity of the carbon uptake in real cases. These factors can be, majorly divided into two different categories. Some of them are internals, like the concrete mix designs, the constituents, the binder type and content, the water to binder ratio, or some of them are external factors such as the exposed surface area, the exposure condition, or the climate conditions over there. I'm going to bring some examples from different studies that have experimentally investigated the impacts of all these factors on concrete carbon uptake and how it can be different from a, let's say, a control or plain concrete mixture. First, I'll start about the effect of alternative binders and water to binder ratio. Here on this graph, you can see that on the y-axis, we have the rate of carbonation coefficient to plain PC. When it is 1, it means that it equals to the rate of carbonation coefficient that the plain Portland cement without any pozzolanic materials or alternative binder has. And here on the x-axis, you can see the clinker replacement level from 0, obviously, up to 80%. And each curve and each dot represents one type of alternative binders or supplementary cementitious materials. Like the green one is fly ash with 2 different water to binder ratios, and we have silica film, the purple one that you can see that was replaced up to 15% by clinker content, and we also have limestone. And we have the blast furnace slag, the red ones that you can observe here, under the curing conditions for 28 days and the CO2 concentration of 1 to 3%, and also the relative humidity of 55 to 65%. What we can observe here is that once we are replacing these alternative binder materials, the carbonation coefficient will increase and can be tripled compared to the plain Portland cement in the case of, for example, fly ash, once we are replacing 50% of the clinker with fly ash. The same case for blast furnace slag that we can replace up to maybe 80% in different mixtures, and we can see that the carbonation can be increased up to 3 times of the plain Portland cement. So this is one effect. The binder increase, the alternative binder increase in the mixture will increase the carbonation coefficient compared to the plain concrete. The other one is the water to binder ratio, the quantity of the water compared to the quantity of the binder that we have in our mixture. One of the important effects of the carbonation is on the hardened properties of the concrete. But once the concrete is hardened, the permeability of concrete, which is affected by the water cement ratio, will result in the carbonation extent. As you can see, once we are increasing the water to binder ratio from 0.4 to 0.65, the carbonation rate will increase exponentially as a function of the water to binder ratio. And when we have a high water to binder ratio, the concrete will be more prone to carbonation, and there will be a greater depth of carbonation because of the reduced permeability in the binders. Let's go to the next one, which is the curing method and duration. This is another factor. Once we are submerging or once we are curing the concrete after it gets hardened to continue the hydration process, this duration, the concrete curing duration, will affect the carbonation rate. Here is one graph that you can see. On y-axis the carbonation depth, and on x-axis you can see the time. So the square root of time, which here, if you consider it as the number of years, it can be considered up to 3 years. So 3-year experimental investigation of the carbonation depth. And for different cement types, you can see different colors. For 3-day curing in a specific relative humidity, right? Once we increase this curing period from 3 days to 28 days, we can see that the carbonation depth will decrease significantly. Again, it gets back to the permeability of the concrete, analogous to what we observe for the water to binder ratio. And we can see up to 40% difference after 3 years for the carbonation depth once we are increasing the curing from 3 days to 28 days. The next one, after talking about the curing and alternative binders and water binder ratio, is the environmental factors, more specifically the CO2 concentration that can affect the carbonation depth at different ages and at different CO2 concentration. Here is a study that you can see from this graph. The CO2 concentration increase from 3% up to 20% can significantly increase the carbonation depth at different ages of testing, from 7 day to 56 day. What I would like to emphasize here is that in our real case, the CO2 concentration is quite different from the experimental lab setups. More importantly, in rural neighborhoods and in rural area, the CO2 concentration is very close to 0.03%, as opposed to a lab condition that can be up to 0.1%, or in a metropolitan area or in large cities, it can be up to 0.3%. So if you would like to have a good representative model for estimating the carbonation, we definitely need to set up our experimental test in these conditions, but for a longer period of time, because we know that at this CO2 concentration, we may have difficulties to observe significant amount of carbonation. The second environmental factors that I would like to talk about is the relative humidity and the temperature. The relative humidity and temperature both affect significantly, both influence the carbonation depth significantly. As you can see on this graph that shows the carbonation depth on y-axis and the relative humidity on x-axis, the increase in the temperature from 20 degrees of Celsius to 80 degrees of Celsius would significantly increase the carbonation depth. But the other important factor is the relative humidity that you can observe in x-axis. When relative humidity is too low, there is insufficient water in the micropores within the cement paste. That's what we determine, you know, what we quantify, right? And there is low possibility of the formation of carbonic acid in this case. Therefore, we observe near to zero carbonation depth in a very low relative humidity. But on the other hand, when the pores are full of water, let's say in 100% or close to 100% relative humidity, the diffusion of CO2 into the paste is very slow. It is exactly the same case for another type of cement, cement type 5, which has a lower amount of clinker compared to cement type 1 that we can observe in the left graph. And the practical consequence of this relative humidity change is that the carbonation is extremely larger in concrete protected from direct rain, but exposed to moist air. Like when we have a sheltered concrete, but it is, you know, outside, than in concrete that is periodically washed down by rain. Let's say concrete pavements that is, you know, exposed to rain. So that was all about the parameters, that the important parameters that can influence the carbonation rate. And the third part that I would like to, the second part that I would like to talk about is the impact of carbon uptake on concrete properties. First of all, I would like to start with the rebar corrosion in carbonated concrete and the susceptibility of the reinforced concrete to rebar corrosion when we have significant carbonation. You know, concrete is naturally alkaline materials, and there is a significantly severe alkaline medium within the concrete, right? The strongly alkaline nature of calcium hydroxide that we discussed earlier, which has the pH about 13, very close to maximum alkalinity, prevents the corrosion of the steel reinforcement by the formation of a very thin protective layer here, which is composed of iron oxide, and on the metal surface. This iron oxide will be destroyed when the pH of the concrete will fall below about 11. That you can see here that with the pH of 11, we may have 30% of the steel rusted, and it will increase significantly when the pH will be lower than 11. And what is important is that by the consumption of the calcium hydroxide, the pH in concrete will drop significantly to around 9. And this drop, and when the concrete is permeable enough, that carbonation reaches in contact with the steel. So all the layers will be carbonated and steel will be rusted in the presence of water and oxygen. Okay, and the corrosion will occur in the reinforcement rebars here. And the formation of rust that we observe here will increase in volume compared to the original steel that you can see with the red color here, and will eventually result in a swelling pressure that will cause cracking in concrete. In other words, if the full depth of cover here is totally carbonated, the moisture and oxygen can ingress, and the corrosion of steel will possibly result in crack. So that's why that we observe in some of the design codes there are some minimum cover specified for concrete structure. But what I should note here is that the carbonation alone is rarely a source of concern for lifetime, let's say below 50 years, unless concrete quality is very poor and the workmanship is also poor, like insufficient concrete cover as we discussed. But for very longer lasting structures, carbonation must be taken into account and must be modeled in the rebar corrosion and the possibility of the minimum cover specified by these design codes. The next effect of the carbonation on concrete is the increase in the compressive strength. Yeah, you might be surprised to hear that once the concrete is carbonated, the compressive strength of concrete will increase. Like here in this example, you can see that when the specimens are not exposed to any carbonated, any carbonation in the atmosphere, and when we have 3-hour accelerated carbonation with a huge quantity of the carbonation, and 6-hour, we can see that there is an increase in the carbonation in 2 different water to cement ratio. And the carbonation and this increase will result, happens because of the water, which is released from the reaction of the calcium hydroxide, which helps the hydration continue. And the calcium, on the other hand, we have the calcium carbonate, one of the products of the carbonation is deposited in the small voids within the cement paste. So we have like a denser binder in the concrete. Here, this micro structural analysis will show that better when you have a normal concrete or a carbonated concrete. This curve belongs to a normal concrete with compressive strength of 30 megapascal, and this one is a carbonated concrete. And you can see the pore size diameter. So here, the smaller pore size diameter and distribution means that we have a denser matrix and denser binder in hardened concrete. And we are more interested in this region from 10 nanometers to 1,000 nanometers, where those pore sizes play major roles in permeability and mechanical properties of the mixture. This significant drop in the pore sizes and the pore quantity of the mixture, the porosity of the mixture, shows how dense the mixture is and the impact of carbonation in making the mixture denser. The third and last one that I would like to talk about is the concrete shrinkage. The concrete shrinkage will increase as a result of the carbonation. When the hardened concrete is exposed to the carbonation air, the weight of concrete will increase, and there is an irreversible carbonation shrinkage. And we can see that the carbonation increases the shrinkage at intermediate relative humidity again, like once we observe in the results earlier that maximum carbonation will occur at intermediate relative humidity, and maximum carbonation depth also happens at the same rate. So just briefly mentioning why it has happened. Previously, it was perceived that the dissolution, the reaction of calcium and calcium hydroxide under the compression due to the drying shrinkage will result in the formation of a stress-free calcium carbonate. So this is stress-free as opposed to that compressed calcium hydroxide will increase the shrinkage. But now recent studies and many different historical studies show that it's more related to the decalcification of the mixture. Here on the x-axis, you can see the ratio of the calcium to silica reduction of the CSH, the calcium silicate hydrate, and here is the shrinkage. And as you can see, when we have a smaller, we have a more significant drop in the calcium to silica ratio, we have a more significant shrinkage as a result of the carbonation process. So we don't want to go through the details of the chemistry and the calculations, because we just want to know the consequences and the impacts, positive and negative implications of the carbon uptake on the hardened properties of concrete briefly. We will talk also very briefly about the measurement and the estimation of the carbon uptake based on different models. The most conventional method for measuring the carbonation is spraying some pH indicators like phenolphthalein or thymolphthalein, which can be used both in construction sites or in the labs. For those who are not very familiar with that, the carbonation depth was determined by spraying freshly split surfaces with these pH indicators, and we can understand the depth of carbonation by different colors that we can observe here. The carbonated part that you can see here that has pH lower than 9 is colorless, but when the pH is more than 9, for phenolphthalein it's pink here, so we can guess that this part is totally carbonated. But what is important to note that this boundary that we can observe here is this circle, but the pH threshold for starting for corrosion is even larger than below 11 can be considered as where the corrosion can start. So maybe some pink part of this core can be even very susceptible to steel corrosion as well. The second one is more advanced. It's like using advanced analytical methods that we can have access in concrete labs, which is it's definitely more equipment. And the method that I would like to talk about briefly here is the thermogravimetry analysis that we have. Here in this method, briefly speaking, the hydrated cement is heated at a specific rate till reaching more than 1,100 degrees Celsius. And at different ranges of the temperature increase, the dissociation of different hydrated products will be measured. So as we discussed earlier, it's all about the calcium carbonate, right? The calcium, when in the ranges of the temperature that the calcium carbonate is dissociated and completely burned, we can guess, or we can have a good estimation of the mass loss that is attributed to the calcite or the calcium carbonate over there, and we can compare it with a controlled mixture which is not carbonated to understand the amount of calcium carbonate and consequently the amount of CO2 absorbed by the concrete mixtures. Again, it needs a lot of equipment, and once it comes with the aggregate, aggregate also contains some calcite, the limestone aggregate, and it's a little bit difficult to distinguish the calcite in the concrete mixture and the calcite in the aggregate, especially in the interfacial transition zones. So again, we don't go to the details, but I just wanted to introduce these methods that have been developed and have been used in different locations and in different scales for estimating the amount of carbonation. Let's go talk about the numerical modeling. All the numerical modeling that I have known so far, or most of them that has been published, is following the fixed first law of diffusion. For the fixed first law of diffusion, as you can see on the equations on the left, the carbonation depth dc is as a function of k, which is the coefficient of carbonation, and the square root of time. And all the previously developed and reviewed equations for the carbonation follows the same pattern. So we have t to the power of 0.5, which is square root of t, and there are some estimation and differences in the estimation of the k value, because the researchers observed that k depends on multiple criteria, as we discussed earlier. The exposure condition, as you can see, some of them are proposes a different equation for sheltered or unsheltered concrete exposure condition, or for example, the water cement ratio is another thing that concrete researchers have put some difference on that for the estimation of the k value. But what is important is estimation of k needs sophisticated experimental modeling. Therefore, for the purpose of conducting the life cycle assessment or developing an environmental product declaration for concrete, it may not be feasible to have access to this experimental model. Here, it would be a good transition to move forward and to see how the carbon uptake is accounted in different LCA and EPD documents and the product category rules under these EPDs. So far, there is a standardized method in European standards 15804 and 16757 for estimating the use phase, module B, of the carbon uptake. And again, it follows the fixed diffusion law. You have the coefficient of carbonation here to estimate the uptake during the use phase in terms of kilogram CO2, let's say. And this coefficient of carbonation is as a function of the compressive strength and exposure condition in these standards, meaning that there are some predefined values for different compressive strength ranges and the exposure conditions of the concrete elements that will help us, fill in and using the appropriate values for K, the coefficient of carbonation. On the other side, we have the maximum theoretical uptake, the maximum amount of kilogram CO2 that can be absorbed by kilogram binder. Remember, the binder can be, limestone, it can be slag, fly ash, or Portland cement, which is multiplied by the quantity of binder that we have here. And again, the exposure time, the square root of exposure time, and the degree of carbonation. Again, this degree of carbonation will help us, adjust and includes the exposure condition of the concrete. As we talk about, the relative humidity. In low relative humidity, we have some difficulties with the carbonation, and in high relative humidity, we have the same thing. And all these values that will give us the kilogram CO2 per square meter area of concrete will be multiplied by the total area, which will give us the total kilogram CO2 captured during the use phase of the concrete. So here in our center in Concrete Sustainability Hub, we put together a small spreadsheet and use the same methodology discussed in EN standards to quantify the use phase and end-of-life carbon uptake. I will discuss about the end-of-life carbon uptake later, but I just want to give you a preview of the tool and the inputs that you need to fill in and to estimate the total use phase or end-of-life carbon uptake. As you can see, there are two main tables here. The left one is the use phase carbon uptake calculation. The quantity of Portland cement, slag, fly ash, or limestone will be specified here. You have two surface area slots here. The first one is surface area 1, and the surface area 2, for example, when you have a concrete element that has two exposure conditions on different sides, let's say an external wall of a building. From one side, it's exposed to learn, and the other side is indoor. So we have to distinguish between that if you want to calculate the uptake of this exposed wall. Another important parameter, the analysis period, and then again you specify the exposure condition and the compressive strength range of the concrete, and the use phase carbon uptake based on this analysis period will be shown up here. However, for end of life, the user just needs to define the top base diameter and bottom base diameter of the stockpile. I will discuss it later with you. And the crushed concrete grading, we assume that the concrete is going to be recycled and be reused for, as a replacement of virgin aggregates for different applications. The stockpiling time period and the mass of concrete, crushed concrete. We may lose some of those concrete after crushing and grinding. So we have to specify that here, and the end of life carbon uptake will be calculated. So what did we exclude here? Again, it's the same approach that was used in the EN standards. We didn't consider the CO2 concentration in the atmosphere or the temperature fluctuations. So we saw that these two parameters are important to include, but for this purpose, we may not need to go through that much detail. The curing duration of the concrete and the formation of any other product rather than the calcium oxide is not discussed in our analysis. Here are some interesting results that you might want to hear about the Hoover Dam, one of the largest exposed concrete structures in the U.S. with Portland cement content of 225 kilograms CO2, kilogram Portland cement per cubic meter of concrete. And the 28-day strength of 20 megapascal. The construction year was 1935, and here you can see the geometry of the dam and the total amount of concrete used for this. The number of rainy days, we assume that in those rainy days the concrete is totally saturated, so the relative humidity is 100% based on this assumption. And we observe that the historical update up to now, the concrete carbon uptake is around 300 tons, which is equivalent to 0.2% of the emissions coming from the original cement production in 1935. So this is one example. The other example that we used was Rudolph Hall at Yale University. It's an exposed concrete structure, and it's which was constructed in 1963 and follows the Brussels architecture principles, and there's nothing no coating on the outside or the inside of the concrete elements. Therefore we have two types of exposed condition. So we extracted the site plan data by Autodesk Revit software, and we have a precise estimation of the exposed concrete surface area, both internal and external surface area, which was around 10,000 square meter. And we also had the concrete volume around 7,000 cubic meter. And based on the conditions, the number of rainy days that we had in Connecticut, we could estimate that the total amount of uptake since 1963 was around 125 tons CO2, which is equivalent to 5% of the emission from the original cement production. So these are some calculations for the use phase carbon uptake of some concrete elements. But what is more important for us that we have done and we have already published, and that is the life cycle carbon uptake of the US pavement network. For the US concrete pavement, it's a little bit complicated to calculate the carbon uptake precisely. First, the scope is so wide, meaning that we have included all the concrete and composite pavements in the United States. And from one segment to another, the road geometry, the climate conditions, and the concrete constituents are different. The practice, the concrete mix design, and the practice and the amount of binder from one state, from West Coast to East Coast, is totally different. The second one is the maintenance and repair actions. So once we apply the maintenance and repair actions on concrete pavements, we are removing a part of the concrete by, for example, diamond grinding a thin layer, but it will remove the carbonated layer. Or we put an overlay, and a concrete overlay on top of the previously built. Therefore, the age of the surface will become 0 again. So as you can see, when the surface treatment is applied schematically here, we have a small carbonation rate. And when the age becomes 0 again, meaning that we are applying a diamond grinding, the carbonation will start accelerating again and will continue, following the fixed diffusion law. The other thing is that most of the concrete pavements have been built decades ago. So most of the carbonation part has already happened, and the beginning of an analysis period that we have defined here, let's say 2020, we shouldn't take into account the other parts that has been already carbonated once we are starting our network analysis timeline from 2020 till, let's say, 2050. The other part is that once we are periodically apply this maintenance and repair actions, as well as the new construction, we move some of these materials to the end of life. And we may use these concrete elements, this concrete, demolished concrete as aggregates. So we are crushing them, and we have some, concrete that can be carbonated at the end of life. So to overcome these issues, we have defined and we have developed a data analytics and machine learning approach that will help us estimate the total amount of concrete required for concrete pavement, the surface area of the concrete, and the deterioration rate. So the sequence and we can predict the maintenance and repair of the concrete pavements in the future based on the practical maintenance and repair actions in different locations and different regions of the United States. So first of all, we have sampled some input data, like initial road conditions, and we have developed prediction models for deterioration of the and pavement age of the concrete pavements. So in order to assess when and where the maintenance and repair actions should be implemented. Then we divided the whole United States to 10-mile segments, the whole United States pavement network to 10-mile road segments. And based on the prediction models, we have some rough estimation of the maintenance and repair actions based on the budgets that we have predicted for each state at state level until 2050. And based on that, we had a good estimation of the concrete surface area, the square meter area that I discussed in the equations, the concrete surface age, at what age the concrete segment is currently right now, and the demolished and newly constructed concrete volume, so we can have a good estimation of the kilogram binder in different locations. So this bottom-up approach of the carbon uptake calculation will start from the pavement statistics, the input contextualization here. Then we have the individual segment assessments, and once we calculated the uptake during the usage and end of life, we will aggregate the results in the state level and the nationwide level. And what we considered here is the regional mix designs, how it can vary from one state to another, the pavement repair age, the maintenance and repair actions, and the climate conditions in different locations of the United States. This is the approach that we followed for the end of life. What we observed that in the standard 15804, there is no information about how to capture the stockpile shape at the end of life. So we have defined and we assumed that demolished concrete is stockpiled in the shape of a truncated cone, as you can see in this figure. And based on the experimental results that we could observe in the literature, only the 30 centimeter depth of the stockpile can be carbonated. In other words, only this part of the pile, the stockpile can be carbonated, and the particle size, like I said, for recycled concrete can be from 16 to 64 millimeter. So let's go see the results here. First, I would like to share some of the segment level results that we have to show the extent to which the carbonation can be different from one road segment to another. So these three curves represent three different types of roads. The yellow one is an Iowa expressway. The highway in California is shown by the carbon uptake of the California highway, shows here by green color, and the Texas collector is the purple one. So you can see that the collector in Texas has, obviously smaller, surface area. Therefore, the carbon uptake is quite smaller, and the age is maybe 35. So most of the carbonation has already occurred. And as we go forward in time, we don't see that much extensive carbonation. And up to the age of 2027, here we have a composite asphalt, an asphalt overlay on top of the concrete, which will avoid any carbonation in the future because the concrete surface is totally covered. While in Iowa expressways, we have maintenance and repair occurred at age of 2022, and the carbonation will continue, and another maintenance and repair actions happen at 2037 here, which will reset the age of the concrete surface and therefore will increase the carbonation rate. The same maintenance and repair actions happens for the California highway at year 2035 here. So the concrete surface age will reset again, but the extensive surface area of the California highway, the segment that we have here, will show the significance of the annual carbon uptake compared to the other road types in other locations. And here is the national result, the aggregated results that we have for different states on the left part. And on the right part, you can see the total United States uptake, carbon uptake of concrete pavements after 30 years, from year 2020 till 2050. So let's start with the left part. Here in this map, you can see that, again, like any other examples of the roads, Texas and California has the most extensive carbon uptake. And as you can see in the pie chart, most of the uptake comes from the use phase. And that's because, the most extensive concrete pavement networks belong to these two states. While in the state of Illinois or New York, we observed a relatively large carbon uptake, but most of them comes from the end-of-life uptake, the blue part of the pie chart, implying that the composite pavements demolition provides enough materials, enough demolished concrete at the end of life that will give us this possibility to have an extensive carbon uptake at the end of life. Once we sum up all the results here for concrete uptake during the use phase and end of life, we will reach to this graph, this whisker plot chart, that for the use phase, the blue one, and the green one, the end of life, the median value of the carbon uptake is very close to each other. So we can assume that the amount of carbon uptake in the concrete pavement network in the United States at the end of life and at the use phase is very similar to each other. However, we can see the uncertainty related to the calculation of the end of life uptake is quite huge compared to the use phase, and that's because of the geometry of the stockpile that we have. Let's go further and talk about the possibility of increasing this carbon uptake at the end of life. The strategy is to leave these stockpiles for a longer period of time, and you can see that there is a non-linear, there is a non-linearity in the total carbon uptake as we go forward in time. And it's important to note that we don't necessarily need to landfill this concrete for more than 30 years or so, because the uptake will definitely becomes smaller as a function of time when we are stockpiling the concrete at the end of life from 2 years up to, for example, 35 years, again following the diffusion, the fixed diffusion law. And if you want to estimate the cost associated with that, the cost of renting the landfilling site or occupying that landfilling site, that can vary significantly from one location to another. This cost can vary from $20 per ton CO2 savings, what we call it abatement cost, and can be as large as more than $100 per ton CO2 in the future. And here is the current cement carbon capture storage cost that was reported in different policy reports, which is around $75–80 per ton CO2 captured. So for the moment that this technology is still expensive and is still under the development, we can definitely consider the end-of-life uptake as a meaningful and cost-effective strategy to reduce the amount of, to capture the CO2 naturally. So let's go to the conclusion. First of all, we found that the carbon uptake of concrete is a complicated mechanism, and it's influenced by several factors: the binder, the external factors like environment. The second one, the US pavement network can absorb around 5% of the carbon emissions from the cement production. The total amount of those Whisker plot chart corresponds to 5% of this total cement production emissions that we calculated. The use and end-of-life carbon uptake of concrete of pavement network can be quite similar and in the same range. And at the end, the abatement cost of carbon uptake can be lower than the current CCS or CCU cost of cement, those technologies that are implemented on cement and concrete industry. So for the future studies, we propose to apply the same bottom-up approach or similar bottom-up approach to estimate the total carbon uptake of buildings or other infrastructure systems. And we also propose to develop reliable models to include climate change impacts in the analysis, including the temperature fluctuations in the future, the precipitation changes, and the CO2 concentration in that small ranges that we discussed. And the last part is the optimization of the carbon uptake. So for many different concrete structures that are not reinforced, like concrete pavements, the jointed plain concrete pavements that doesn't have any reinforcement except for the the dowel bars, which are not majorly affected by concrete properties. And we don't see any negative effect on concrete durability because of the carbonation. We can consider and we can change the exposure conditions, the relative humidity part, or the binder type and content, or the exposed area of the concrete structure. What we can see is more flexible for architects, and the end of life spreading. So we can leave those demolished concrete for a longer period of time at the end of life to improve or to increase the carbon uptake of concrete without compromising the concrete durability. However, we discussed that it's 5.5% of the emitted CO2 that can be inhaled by this concrete pavement that we have. Still, 94.5% of the emitted CO2 from cement production is out there. Therefore, we definitely need to implement and think about alternative strategies to reduce this 94.5% of the emissions or compensate this amount of CO2 through different policies and strategies. Thank you so much. It was all what I wanted to present today for you, and I'd be glad to take any questions as well.
Great. Thanks very much, Hassam. There's a lot of interest in the work that you've done. We got a lot of questions that came in, and so I'll try to get to some of them in the time that we have here. I'd say one of the questions, since you just showed your, your 5.5% there, which just relates to concrete pavements in the US, right? And one of the questions is, there's another paper that came out a few years ago that talked about, that carbon uptake offsets about 43% of CO2 emissions. So there are differences in scope of those different numbers. Maybe you could explain, what are some of the differences in scope, and then what that might explain some of those differences.
Sure, that was a great question. We saw different numbers in the literature, and we saw different ranges, estimated by different researchers. First of all, the scope, as Jeremy mentioned, the scope of analysis is quite different from those studies and us. In our study, we consider only concrete pavements. In many different studies, they consider different types of concrete structures. The other important thing that we noticed is that most of the conducted carbon uptake estimations follow the top-down approach, meaning that they couldn't capture the exact geometry or the mix design or the level of details that we have incorporated. In our analysis, we individually assess and track the carbon uptake or the maintenance and repair actions or reconstruction of the concrete segments, concrete pavement segments in the United States, but some other studies try to use a bottom-up approach that cannot capture all these details. So first of all, the scope of analysis, and second, I would say the approach that we have chosen for and developed for this analysis.
And I think another key point is that in that one paper, the Nature Geosciences paper, their 43% is just based on what we call process emissions of cement. Right.
Exactly.
Whereas your 5% includes all emissions. So maybe a closer equivalent for them would be, approximately half, right? So 20-ish% actually is what they're estimating when it comes to total CO2 emissions.
Exactly.
Great. Okay. And while we're talking about our estimate on pavements, there are a few questions about how you're dealing with the fact that, a lot of concrete pavements have asphalt overlays. Which would affect that. Can you talk about how you accounted for those asphalt overlays in your analysis and how that affected the carbonation?
So generally speaking, first of all, we exclude the use uptake for those asphalt overlaid composite pavements, meaning that we didn't consider that there is any uptake happening over there. Well, we know that there might be some uptakes, but to be conservative here, we consider that if there is no exposed surface area for the concrete and if it is covered by another polymer or materials, there is no use-based uptake. But like I mentioned briefly in the presentation, during the presentation, the maintenance and repair actions and strategies that we could obtain from different life cycle costing documents of different states for different regions gave us some ideas when and where the maintenance and repair actions happen. So once the composite pavements are demolished at the end of life, after 50, 70 years of the service, we consider that those demolished concrete will be moved to the recycling plant and will be crushed and grinded to small sizes to be used as an aggregate again. So those volume of concrete is those, the carbon uptake of those concrete volumes are attributed to the composite pavements in those segments.
Yeah, so exactly. So we account for the fact that when you put asphalt over it during the use phase, there's no longer any carbon uptake. But at end of life, that's where when they're crushed and then that concrete is exposed is where there is carbon uptake. So Okay, there's two kind of follow-up questions to both of those. Some people said, in some concrete applications, you end up using sealers on top of the concrete. What's your sense on how that would affect carbon uptake?
Well, as far as I know, the any different types of any different coatings can uh, can result in different rate of carbonation. Some of the coatings can even accelerate the carbonation. For example, some research studies recently shown that using different nano titanium dioxide coatings on concrete pavements or concrete structures can accelerate the carbon uptake of concrete, and even using that in the mixture as well. Depending on the composition of the sealers or the coatings that we apply to concrete surface, we can expect different directions of change in the carbon uptake of the concrete pavements.
Got it. So it goes back to sort of your point that what we're trying to look for is balancing these issues around performance. Performance, obviously, we want durable concrete, but now we have this opportunity to maybe look at how can you do that while simultaneously enabling the carbon uptake as well. And maybe you don't maximize that because of durability concerns, but it's certainly something you can design for as well.
Exactly.
Great. There were also some questions about, what kind of carbonation do you get if you're using recycled concrete aggregates? If you have some of this crushed concrete, and with those aggregates, do you have any information on how that would affect the amount of carbon uptake?
Well, if there's any parameters that changes the durability or the permeability of the mixtures, it would definitely affect the carbonation rate as well. So one important idea is to investigate experimentally what would be the implications of using recycled concrete aggregate in the mixture in terms of the permeability.
Great. We had a question about a fly ash, and basically it says if fly ash reacts with concrete calcium hydroxide and reduces its content, it seems counterintuitive that more fly ash would lead to more carbonation. And this was pretty early on in the presentation, I think, when you're presenting some other research results. What are your thoughts on that?
That's a good point to mention here. To answer this question, once we increase the quantity of fly ash, we will definitely change different parameters. Some of them are physical and some of them are chemical. The quantity of calcium oxide in fly ash is comparatively lower than the clinker or Portland cement, let's say. Therefore, we may it may perceive that it may be perceived that the carbonation is lower, but in the incorporation of fly ash in concrete mixture can affect the permeability of the concrete. Or in other words, you can see that there are some correction factors in different product category rules that give a penalty or give an increase in the carbon uptake of the concrete incorporating fly ash or even slag or limestone as well. So yes, one part is the chemical properties and the availability of the calcium oxide in the binder contents, and the other part is how it's being reacted over there. Like 50% fly ash replacement by clinker would definitely reduce the the permeability, have the negative effect on the permeability or compressive strength of the mixture indirectly. So
great. All right, well, we're at time, and we had a few other questions we weren't able to get to. You see on the screen here, cshub@mit.edu. That's an email you can use to contact us with questions. A few questions we got will this recorded presentation be available? And the answer is yes. There'll be a follow-up after this when that recording is available, which should be in the next day or two. Also, people were interested in the calculator that Hassam mentioned and copies of the slides. You can also contact us via that way for access to both of those. We're glad to share them. With that, thanks again, Hassam, for helping us navigate this sort of complicated issue of trying to deal with both durability on one hand and also carbon uptake on the other. And it's clear that there's still a lot of opportunity to explore this and try and optimize both of those together. So thanks again to you, Hassam, and thanks to everyone for joining us. And we hope you'll join us again at a future webinar. Bye-bye.
Thanks so much. Thanks, everyone.